Hello everyone. Today I would like to share about system noise temperature, and G by T ratio. To know about the system noise temperature, here we are considering the receiver model of super heterodyne receiver. In our previous classes, we already know about the super heterodyne receiver. Super heterodyne receiver consists of three main parts. First one is it consists of RF amplifier section. Second is it consists of a mixer. It consists of an IF amplifier section. These are the three main parts of super heterodyne receiver. So here to derive the noise temperature, we are considering the super heterodyne receiver model. For that, here we can see this is the noise model of our receiver. The incoming signal, it is the T in is the temperature, noise temperature of the incoming signal. And here TRF is the noise temperature of RF amplifier. GRF is the gain of RF amplifier section. Now the second section is mixer. TM is the temperature of mixer. GM is the gain of mixer network. TIF is the temperature of noise temperature of intermediate amplifier, IF amplifier, intermediate frequency amplifier. GIF is the gain of IF amplifier. So this is the complete noise model of our receiver. This is the complete noise model of our receiver. Here the noise components in each and every block, that is in RF section, in mixer section, and in IF amplifier section, all the blocks here we are replacing with that particular gains and noise temperatures. Now the total noise power, here we can see the total noise power Pn at the output of the receiver. Total noise power at the output of the receiver is given by, here we can see Pn is equal to GIF into K. Here K is the Boltzmann constant. GIF is the gain of, here we can see gain of the intermediate, sorry, not this one. I think it is the, this is the intermediate amplifier section gain of intermediate amplifier, and TIF is the temperature, noise temperature of the intermediate amplifier section. So here it is GIF into K. K is the Boltzmann constant into TIF. TIF is the noise temperature of the intermediate amplifier, and BN. BN is the noise bandwidth. This component plus, here we have two more components, that is mixer section. Coming to the mixer section, here these gains will multiply here because these two are in cascaded. So this gain GIF multiplied with GM into again K. K is the Boltzmann constant, and TM. Here TM is the noise temperature of the mixer, and BN again is the noise bandwidth, plus one more component we have, that is RF amplifier section. So here the gains GIF, GM and GRF into K. K is the Boltzmann constant again into multiplied by, here we have two noise sources, that is TRF plus Tin multiplied with noise bandwidth. In this way, we had written the total noise power at the output of the receiver. This is Pn. Now, this Pn is equal to, here we are taking the terms as common from these three terms, GIF and GM. Here we can see, we can take the common GIF and GM. And here we can take the common GIF, GM and GRF. So these three terms we are taking as common terms. And the equation is simplified like this. And from this equation, again, we are taking K into Bn also as a common term. And final equation, we are getting like this. This is the complete noise power Pn, which is obtained at the output of the receiver of noise model receiver. Here, this term, this term which is in bracket, that is TRF plus Tin plus Tm by GRF plus TIF by GM into GRF. This term is called system noise temperature. It is called system noise temperature, TS. System noise temperature. Why? Because this temperature terms represents complete components of the system: RF amplifier section, intermediate frequency, and mixer. So this is the system noise temperature, TS. So this term here we are replacing with TS. So the noise power becomes this one. That is GM into GIF into GRF into K into TS into Pn. So this is the system noise temperature. Hence, the equivalent noise temperature is given by that complete term TS is equal to TRF plus Tin plus Tm by GRF plus TIF by this one. And now, when the RF amplifier in the receiver front end has high gain, the noise contribution by the IF amplifier and latter stages can be ignored. Here, when the RF amplifier in the receiver front end has high gain, we know that the first block of our receiver will be the RF amplifier. So if the gain of the RF amplifier is high, the noise contributed by the IF amplifier and the latter stages can be ignored, and the system noise temperature is simply the sum of antenna noise temperature and low noise amplifier. Here, if the RF amplifier has a high gain, front end RF amplifier has high gain, we can neglect these two terms. Why? Because high gain, if gain is more, this parameter will become, this denominator will becomes large. And here also the denominator term will becomes large. So these two components we can neglect. So the TS will be equal to, then the TS will be equal to TRF plus Tin. TRF plus Tin. So here this Tin is nothing but T antenna. This Tin is nothing but T antenna, and TLNA is nothing but TRF. Tin is nothing but the incoming signal temperature, noise temperature. So that is nothing but which is coming from the antenna. So this Tin we are replacing with the T antenna, and this TRF is nothing but the low noise amplifier. Here LNA represents the low noise low noise amplifier. Low noise amplifier. So this TN is replaced by T antenna and TRF is replaced by TLNA. Therefore, the system noise temperature is given by TS is equal to T antenna plus TLNA.